I'd like to welcome everybody to our party. My name is Joe Chambers. I'm Chief of the Flight Applications Division here at Langley. And it certainly occurred to us as we reached the end of a 32-year career of this illustrious airplane that it certainly wasn't worth just rolling it out the door, and decided to have a little celebration. And I hope all of you enjoy it, have a good time, and maybe learn a little bit something about the F-106 and about our airplane in particular. I'm glad everybody showed up. We've got a few guests that I hope show up late. That's some of Norm Crable's storm hazard, severe storms. I hope they show up after we're through this afternoon. At this point, what I'd like to do is introduce Richard Peterson, the director of the Langley Research Center, for his welcome comments.
Thank you, Joe. Let me add my personal welcome to all of you here today. Welcome especially to everyone who worked with this historic aircraft. While we're focusing our attention today on the flying hardware, the aircraft we at Langley call NASA 816, the real kudos go to the men and women who made it possible for 816 to fly and to do its work. We're honored to have many of them here with us this afternoon. We're also honored to have several special guests with us, including the Mayor of Hampton, Mayor Jimmy Eason. On my sheet is the Vice Mayor, Mel Butler, and I haven't seen Mel. I hope he does get here, but he may not. He's an old friend of ours here at Langley. And from the Virginia Air and Space Center, the president of the center, Tom Chisman, the director of the center, Ralph Johnson, and board member Ray Bottom. We also welcome a number of guests from the Air Force, from NASA headquarters, the Lewis Research Center, Wallops Flight Facility, and the Smithsonian National Air and Space Museum. We're pleased that you're with us this afternoon to pay tribute to NASA 816 and the NASA 816 team. This historic aircraft made many outstanding and unique contributions in its more than 30 years of service, both with the Department of Defense and with NASA. As you'll read in the souvenir pamphlet, the Air Force used NASA 816. Of course, they didn't call it by that name, to evaluate new modifications before they went on to the fleet airplanes. Lewis Research Center used 816 to study supersonic propulsion systems. Langley first flew 816 to study the effects of in-flight lightning strikes on the aircraft, and then to study the aerodynamic effects of a wing modification, all of which you'll hear more about later. In addition to its significance as a test vehicle, this aircraft just made the last manned flight of an F-106. The Air Force F-106s have been converted to target drones. They are still flying unpiloted for obvious reasons. As you'll hear later, this aircraft design has special significance to Langley Research Center. Langley's Richard Whitcomb, who is here today, was instrumental in reshaping the aircraft that would eventually become the F-106, resulting in a revolutionary advance in aircraft design. I want to welcome everyone to this special gathering and recount with the people who were there, the story of the F-106, and in particular, this unique airframe. To bring you the first part of that story, here is Joe Chambers. Joe?
Thank you, Pete. This occasion is historic, very historic, for three different separate reasons, as Pete alluded to. First, this is a story that you rarely see in aeronautical history, the fact of the last of a 35-year run of production airplanes returning back to a research lab that had a significant impact on the development of the aircraft. Second, this specific airplane, through its career, exemplifies the capabilities, the innovations, the dedication of NASA, not only here at this distinguished research center, but also our sister center, the Lewis Research Center, and of course our brethren, the Wallops Flight Center as well. The third historic occasion is that we will symbolically retire this airplane today to a world-class, up-and-coming air and space museum right here in our own backyard in Hampton. And it's a pleasure for NASA to be able to make this action. Now, to get into the agenda and the program, what we're going to try and do, I'd ask you to look at your the black insert in your souvenir program. For those of you that are colorblind, it's still black. I do have one minor agenda change to make here. Jim Day, the F-106 Convair rep, has a conflict. Couldn't make it with us today, but not to fear. We've done the homework, and yours truly will cover the Air Force years. At the onset, I'd like to say I'd love to have everybody associated with each program cross the stage, but I don't think it would bear the weight. So we've chosen a representative, although not unworthy person, to be able to come up and talk to the programs. So I hope you enjoy that. Over the next hour, basically, as you can see in the agenda, what we'd like to do is retire one of the most important legends and retell one of the most important legends in aeronautical history in this country, and certainly at the Langley Research Center in terms of area rule. We'd like to trace the history and some of the technical programs that this particular airplane has been involved in throughout its distinguished career, symbolically retire this airplane to the new Air and Space Center. And as part of this process, we've taken the occasion to retire one of our most loved NASA people who have made this airplane go for the last history since it's been here at Langley. And finally, before I forget it this time, I want to remind people that after the ceremony, there will be a photo-taking session by the airplane, and I'll say more about that at the end of the program. So you can see we've got a lot to do to squeeze about 32 years of history into about an hour. And I've asked the speakers to try and keep to their time on penalty of death. Norm Crable is sitting over there saying, yeah, Joe, I know. I'd like to begin talking about the airplane itself. In my 29 years here at the center, I've retired a lot of people emceeing retirement parties. But this is the first time I've ever retired an airplane. And all you females out in the audience, I'm sorry, but you'll have to provide me the liberty of referring to it as a her. And with that history of retirements in mind, I've got to look at it as I would a female that I'm retiring from the Langley Research Center. The airplane itself, when you look at it, first thought I have is that this is going to be the heaviest female I've ever retired. Interesting, we don't need to take the time to do our usual presentation of NASA wings or NACA wings, because this retiree brought its own wings today. Even though she's 30 years old, it's a beautiful airplane. You can see the curves, the Mae West or Marilyn Monroe waist on the airplane, which is really a statement of the ability of our crews to keep the airplane in such a pristine state. So although she's over 30 years old, which is probably 400 years old in dog lives, it's a remarkable airplane. But we all know that retirement parties have to be a mixture of kudos and a little bit of roasting. So when I look at this airplane and again think of some of the females I've retired, I just have a couple of observations. First of all, for a female retiree, boy, she really needs a nose job, no question about that. And I don't know how many of you are really aware of the vices that this female has. She's a habitual heavy drinker, very high octane fluids. And probably the most embarrassing vice that this retiree has is the fact that she's always really had a real bad problem with exhaust gases. We'd like to start off the ceremony by recalling one of the most important aeronautical legends here at this center, the one that Pete alluded to earlier involving Dick Wickham and the development of the area rule. By way of introduction, I'd like to say a few words. This story begins back in the 1950s, so for all you younger people, we older people will turn our heads so you can return to the womb, because this was long before you were a gleam in somebody's eye. But the story really involves three different ingredients. The first was basically the general interest and, frankly, the unknowns in how best to shape airplanes for high-speed flight. The second one was the development of testing techniques to get good, accurate prediction of aircraft performance at transonic and supersonic speeds. And the third was basically a widespread paranoia and perception of a general threat to the United States from the Soviet Union in terms of nuclear bombers. First, I'd like to talk about the issues of high-speed airplane design. This first slide indicates some of the thoughts that went into how airplanes were proposed to be designed for high-speed flight. This basically shows an idea of the Convair company. They had a great interest in looking through the German World War II data in highly swept wings, and in particular some of the German information on delta wing airplanes. The Germans never flew a delta wing airplane. But they were able to, the Convair company was able to work with some of the Germans, in particular Alexander Lippisch, the designer of the Me-163 rocket-powered airplane from World War II, and basically designed this airplane to evaluate the handling characteristics of delta wing airplanes. This is the XF-92A. It was put together from 5 different airplanes to try and hurry the program on, and it basically was restricted to subsonic flight, made its first flight back in 1948, and flew quite satisfactorily in terms of its handling characteristics. So the promise of the delta wing as an input to overcome the hurdles of high-speed flight was predominant on the list of thinking in the U.S. at that time. However, along with that was the concern over accurate projection of transonic performance, in particular drag prediction. The next chart shows 2 things that I want to mention about that era. The first is that there was considerable concern about wind tunnel testing to measure transonic performance. As most of you know, the Langley Research Center in that same time era had developed a slotted configuration for the 8-foot transonic tunnel, achieving the Collier Trophy Award to Langley for that achievement. However, there was still great concern about the fact that wind tunnel walls reflected shocks and basically gave erroneous data at transonic and supersonic speeds. So other testing techniques were devised, putting models on the upper surface of wings of aircraft, and as shown here, rocket-boosted models that were tested at the Wallops Island facility under NACA direction. This particular photograph, though, shows one other thing I'd like to call to your attention. You can see that the model, which is a generic airplane shape, makes use of that delta wing principle we saw on the XF-92. But if you look at the fuselage, you can see what designers thought was going to be the efficient supersonic airplane of the future. If bullets went fast, obviously airplanes should be shaped like bullets. So this projectile shape was foremost on the mind of a number of airplane designers at the time in terms of how to design supersonic type airplanes. The plot then begins to thicken. There was a paranoia back in the 50s about the Russians attacking the U.S. If you were like me and you grew up in elementary school in those days, every Friday afternoon was spent underneath your school desk simulating nuclear attack from the Russians. I can't believe we thought we were going to be saved, but we certainly hid under those desks. The probability of that Russian attack was a real foregone conclusion in a lot of military planners' minds at the time, and led to the need for a high-speed military interceptor, one that could go out, shoot down the Russian bombers before they got to the United States. So competition was held for the design of such an airplane. The next slide basically shows that Convair was the winner of that competition, and they built an aircraft referred to as the YF-102. You can look at it and quickly see that it adhered to some of the philosophy, the delta wings, the rather projectile-shaped fuselage, and the Convair engineers certainly thought they had the problem licked. They had adhered to all the known design practices at the time, and there was no concern on their part that this airplane would not be the high-speed savior the U.S. needed. By 1952, the Air Force had contracted for 2 prototypes of this airplane, and they were gearing up a production line out at San Diego to turn out hundreds more of the airplane. However, as shown on the next chart, some of the testing that was underway at Wallops with the rocket-propelled model of the F-102, and also testing done in the newly modified 8-foot tunnel here at Langley gave some pretty ominous signs. Predictions that this airplane was not going to be the high-speed savior the country desired. In fact, this airplane was not going to be capable of exceeding the speed of sound in level flight. So needless to say, there was a great deal of gnashing of teeth, and as shown in the next chart, Mr. Richard Whitcomb of the NASA NACA Langley Memorial Lab became involved in that entire process. The legend is here, and I'd like for Dick to come up and relate what happened from that point on. Dick?
As Joe said, the data showed that the drag was way too high. And it wasn't just the 102. There were a number of other airplanes that had drag that was way too high. So in the 8-foot tunnel, we decided to run some flow studies around a typical configuration to see what was going on, because none of the theories predicted this high drag. And with the flow studies, looking at the Cheran pictures, which we got from the flow studies, and from thinking about what Boosman had been saying, we came up with a new approach to predicting transonic drag. It's called the area rule, and it's called that because it relates the transonic drag rise to the cross-sectional areas of the airplane. That is, you slice the airplane up like an apple along cross-sections normal to the airstream, and then plot up the areas, and it's that area distribution that predicts the transonic drag. A very elementary theory, but it works. We went through and compared all the data, and sure enough, it worked. We then went into a program to demonstrate this. That is by testing various bodies that had different area distributions. But the more important thing that this allowed us to do was to reduce the drag. If the drag is a function of that area distribution, then if you make the area distribution nice and smooth, remember Joe said something about the fuselage should be in a bullet shape. What really counts is to make the area distribution for the total airplane bullet shaped. And when you do that, you end up with an indentation in the side of the fuselage to offset the area, cross-sectional areas of the wing. Well, very elementary, and we tested it, and sure enough, the drag for our experimental body, the wing drag, just disappeared. The drag for the total airplane would come down by 50% at least. So this occurred at just about the time that they decided that the 102 had way, way too much drag. So then the fun started, because we talked with the Convair people about redesigning the airplane with an indented fuselage. And so they were willing to go along with us that far, that is to redesign the model. And so they provided us with a new model, which they said, of an airplane which they said they could build. And sure enough, with that indented fuselage, the drag would come down substantially. Now, I think it's about time to put the slide up. That is the, would you go to the next one, please. That's the one I want. The picture here is of the original up at the top, and then the indented fuselage at the bottom. I'd like to point out here, or add here, that the Convair people at this point codenamed that redesigned airplane the Marilyn Monroe. And I think that, well, maybe there's some young people who've never heard of Marilyn Monroe, but anyway, she was really big in those days, just like Madonna is these days. So it has the indentation. Now, that was what we tested that in the tunnel. And of course, as I say, the drag came down. Then we got together with the Convair management. And the Convair management did what management's been doing ever since I worked in the aviation industry. They tried to get out of changing things. They said, well, why don't we change the requirements? The Air Force says, no. Anyway, let's get into this. There was a big battle, and finally the guy that was a project engineer at Wright Field on the project said to Convair, either you change that or the contract is canceled. Now that gets their attention. And so they went ahead and started changing the real airplane, going through the process of the redesign of the fuselage and building a new fuselage. I was out there at the time they were building the new fuselage, and I have never seen anything quite like it. Workers were swarming over that new fuselage like ants. They were all over the place. You couldn't even see the fuselage, but there's so many workers on it because they had to do it fast. And so they built the new fuselage and went out and flew the airplane. And sure enough, with the change in the design, it went through the speed of sound while climbing, whereas the original one could not even get through the speed of sound. So this really set the ball rolling, and they started changing the production line. Now, that is very, very briefly what happened on the area rule change. But then later on, they had a new engine, and so they decided that they would we're going to put the new engine in the airplane. Could have the next slide, please. Now, I'm using this shows the original airplane at the top, then the 102 here. And then they decided, well, if they were going to put a new engine in, let's do more than that. And so they totally redesigned things. It was essentially a new airplane. That's why it got a new number. Not only did the first thing they did was to greatly increase the indentation. The indentation on the original 102, on the 102 was not deep enough, and so now they made it deep enough to get some better drag reduction. In addition, they did a change in the wing. Over the years between the 102 and what became the 106, the Ames people had been working on conical camber, which was a means for reducing drag due to lift and improving the high lift characteristics. And if you look at the airplane over there, you can see the conical camber, particularly at the tip of the wing. Everybody ought to go take a look at that and see what that conical camber looks like. It had a big effect on the higher lift characteristics. And that was put in the airplane too. So now they had an airplane, when they finally flew it, which was substantially better than the 102, technically. And of course it had a more powerful engine, and it went to a substantially higher speed. But I had very little to do with, or Langley had very little to do with that whole redesign from the 102 to the 106. And so that's how we arrived at the 106. And so now I'll turn it back to Joe.
Being the modest guy he is, Dick didn't want me to show this view graph, but I will anyway. The Collier Trophy, those of you that don't know, is presented for the greatest achievement in aeronautics in the United States of America. And Dick brought this trophy home to Langley in 1954 as a result of his contribution with the area room. Tremendous accomplishment, one that we're proud of. For those of you that will be visiting the new museum in the future, the Collier Trophy replicas that are currently on display in our visitor center will be moved over to the new museum, so you'll have a chance to see them down there as well. Slide off, Ken. I did want to make one comment to Dick. He did such a beautiful job of showing people how airplanes should be designed. Elegant, beautiful airplanes. We've seen examples of those through the years. And I just had one comment to make, as shown on our next view graph. Some of the current airplane designers really need to go back and think about that, Dick. In fact, it is ironic because, as you well know, Ben Rich and the design team won the Collier Trophy for this airplane. So beauty is in the eye of the beholder, I guess. I'd like to talk a little now about next chart, Ken. About the 106 production, of course, from that troubled past, the F-106 came forth and served the country well in terms of service with the Air Force, ADC, as well as the Air Guard. 340 types of this airplane were built. By the way, over 800 F-102s were built, so far fewer F-106s were built. But it was to be the last word in the manned interceptor world. This airplane, the F-106, was used to set the world speed record in 1959. It was flown 1,525 miles an hour, Mach 2.41. A few years later, as you know, the speed record was eclipsed by the Russian MiG-25, and as everybody knows now, the Lockheed SR-71 Blackbird holds the world speed record. What most people don't know, though, is that for a single-engine production airplane, the F-106, this 25-year-old airplane, still owns the world speed record. Convair built 63 models of the B, which is the two-place version, which of course 816 is. And our distinguished retiree was rolled out on the production line. It was procured in 1957, and it rolled out on the production line in 1958. Now, Ken, if you'll turn the slides off for a minute, I'd like to direct our attention to the airplane. I'd like to test the young people just to show you how old this airplane really is. I went through the World Book Encyclopedia the other night looking at the year 1958, and it was interesting to see how much has changed in the world. We can play a trivia game. If you know the answers, you might yell them out. I'll start with an easy one. There was a new agency formulated that year with a grand budget of $300 million. We all know which one that was. The president, of course, was Dwight Eisenhower when this airplane rolled off. You may not be familiar with the fact that in 1958, the first transatlantic jet service was put into operation. And I bet you can't guess either the airline or the airplane that started that work. It was the British Comet, and it was British Overseas Airways that started the activity. Pan American started its first New York to Paris flight in 1958. The time, which previously was a 12-hour flight using a propeller airplane from New York to Paris, was shortened to 7 hours with the introduction of the 707. And that year in aeronautics, there was a new research airplane that rolled out in October of 1958, which you'll recognize as the X-15. So the airplane you're looking at today rolled out several months prior to the X-15. And of course, we all know the X-15 has been hanging up in the Smithsonian for some time now. There were some other interesting non-aeronautical activities in 1958, just for the benefit of you youngsters. President Eisenhower asked the congressional approval to begin the construction of a sports stadium near the National Army. Of course, that ended up being JFK Stadium and where the Redskins play today. There was only one company in the world in 1958 that was producing color television receivers, and the outlook was extremely grim. People told RCA they should be out of the business and NBC that they should be out of the business. Two fellows named Nikita Khrushchev and Fidel Castro took over power in 1958, and President Eisenhower signed what was called the Federal Highway Act for a dream called the Interstate Highway System. And the funds would come basically from the federal excise tax on gasoline, which had been raised to 3 cents a gallon. Maybe to put it in best posture for everybody here, the average NACA branch head in 1958 was making about $4,000 a year. So when this airplane rolled out, it was indeed quite a while ago. Now, if I can have the next chart, Ken, we'd like to recount what this airplane has been through in 32 years and hit some of the highlights, starting with its initial operation for the Air Force. This has been one of the most difficult ones to research for the particular airplane. The next picture is one that we have located showing the airplane in a hangar in its original Air Force markings. The airplane served as a R&D and development airplane for the Air Force at several Air Force bases, including Edwards, Tyndall, Holloman, Geiger Field in Spokane, Washington, and McClellan Air Force Base. And it's been hard for us to track what happened to the aircraft. Anyone who has a clue as to what that gizmo is on the left wing, we'd love to know. We thought at one time it might be an infrared sensor or whatever, but we haven't been able to identify it. What I have been able to do is some homework as to what happened to the airplane, again, in its Air Force years, because it was called into service down to General Dynamics. The next slide in fact, depicts the fact that this particular airplane, our retiree, was a major key player in the development of the F-111. This airplane was called down to General Dynamics in 1964. They took all the avionics out of the airplane and replaced it to test the F-111 terrain following avionics system, which enables the current F-111 to fly down to 100 feet or less altitude and hug the terrain. While it was down there, in addition to that work, they did the F-111 stick grip development, which is different than the F-106. And it became the personal airplane of Phil Ostreicher, who's currently the head of flight operations at General Dynamics, during chase flights over the Gulf for the F-111 in this development program. Phil, many of you will remember, is famous for his inadvertent first flight of the YF-16 out at Edwards when the F-16 program got started. So the airplane really had a heyday down at General Dynamics in terms of what it was doing during the F-111 program. Following that activity, the airplane basically was delivered to NASA Lewis for a program at Lewis. The next slide depicts the airplane as it arrived at Lewis. You can see it in its Air Force markings with its original tail number. The next chart depicts the NASA meatball and what happened to the airplane. We changed the last numbers from 2516 to 616, and I like for you to pay attention to these numbers as we go through. Each NASA center has a lead number for its airplanes. Langley's is 5, so our airplanes tend to be 515, etc. At Lewis, they have 6. So 616 was the airplane at Lewis, and at this point, I'd like Fred Wilcox, who's with us today from Lewis, to recount what the airplane was used for back during its Lewis heyday.
Well, thanks, Joe. I've been to a lot of retirement parties, too, and this is the first time I ever went to one for an airplane. So, happy retirement, F-106. You did a super job for us. You were a member of a team that was supposed to go out and learn something about how to build this airplane on the slide. This supersonic transport was being considered, and Lewis was given the job of working on the propulsion system. Data was lacking in the speed range from Mach 9/10 to 1.3, and that was because there weren't any wind tunnels big enough to test one of these nacelles under the wing with an inlet in front, exhaust nozzle in the back, and a section of the wing above it. And until we could test this nacelle, we had no way to know what the performance would be. So Lewis director Dr. Abe Silverstein got the idea, why don't we find an airplane that we can put a couple of these nacelles on and fly them? And he set up a project, Milt Beheim as the project manager, and people from all over Lewis as members of the team. And they were procurement people, instrumentation people from 2 wind tunnels, 2 ground test facilities, just a lot of people. It was a fun team to be on. The goals were bold, and the coaching was great. Everybody did their best, and then we signed up our star player, F-106 over here. When you came in to us, you were tail number 516 from Carswell Air Force Base, Fort Worth, Texas. You came in on the eve of Halloween, 1966. We later changed your tail number to 616, and we started modifying you by taking out your weapon system. And that included over 700 pounds of wiring. We added these 2 nacelles that each had a J-85 engine. We put in a fuel tank in the missile bay. We put in a data system, and this data system would scan pressures with scanning valves, and it took 11.6 seconds to run through a reading. Okay. Yeah, part of your elevons were cut out to make room for the nacelles, and there were 2 nacelles. This one had a research inlet and a research nozzle. This one was a reference nacelle. It had an open nose inlet and a cylindrical nozzle. The two test engines were operated from the back seat. The main engine was operated from the front seat. So that took careful coordination by your two pilots to hold the speed steady during the data scan. But no matter what speed we called for, you held it, even when it was near Mach 1. And we flew you in two supersonic corridors, one over Lake Erie and one over Lake Huron. We had a chase plane that would follow close behind and tell your pilots how things were going with the test engine. Remember the time you were accelerating up to Mach 1.5 and your pilots put all three engines in afterburner? Boy, did you walk away from that 104. And one time when we were calibrating your nose boom, we flew you 50 feet off the ground at 600 knots. You flew over 300 research flights, and on most of those you came back with only enough fuel for one go-around. And more than once you came back flying on your research engines with your main one throttled. All of the changes that we made raised your gross weight to the highest that you'd probably ever flown. The exhaust nozzles limited the permissible angle of attack on landing. So we flew the approaches at 10 degrees angle of attack and 200 knots. You gave us a few anxious moments when that test engine came apart in flight. And the other time when the tire blew on landing. That put you in intensive care. But you came back. And we at Lewis, who have known you for 25 years, to a person proudly say, this plane has guts. But enough of that. What about the things we were supposed to learn? Well, after many flights with 4 different inlets and at least a dozen different nozzles, we learned that the nacelles for the supersonic transport benefit from their location under the wing. The inlet is shielded from airplane angle of attack effects. The boat tail drag on the nozzle is lowered, and the flight speed at which the drag begins to rise sharply is raised to Mach 0.98. The air flowing over this section of the wing is expanded, and it recompresses back at the trailing edge. Putting an exhaust nozzle in that area reduces drag. We moved one of the nozzles 10 inches further back and lost that advantage. The nozzle shown here next has a plug in the center. It was a very promising concept for this application. In effect, it puts the boat tail inside the exhaust jet. Well, back in the late 60s, people were beginning to complain about noise near airports. And the proposed supersonic transport was likely to be a very noisy airplane unless careful attention was paid to reducing its exhaust noise. So the F-106 was used in flyover noise tests, which simulated takeoff conditions with various noise suppression nozzles. And we flew over a ground microphone at 200 feet altitude and 250 knots. So that nearly all of the noise would come from the test nozzle. The main engine was at idle. The other J-85 was windmilled, and the test engine was run over a range of power settings. This shows one of the noise suppression nozzles that we tested. It had 104 little tubes that the exhaust came out of. On an operating supersonic transport, these tubes would fold out of the way after takeoff. None of the nozzles that we tested were as effective as we had hoped. Our team also learned some things about nozzles for military planes. These were the planes that would go on their mission at supersonic speed and come back subsonically. They were the F-14, F-15, F-16, and B-1. This nozzle is the nozzle from the F-14 in the subsonic cruise position. Now the F-14 Tomcat, when it takes off with afterburner on, has the nozzle opened up to a larger diameter. They do this by having flaps. And this sharp contour was required in order to store these flaps and the mechanism that it took to move them. The F-14 was flown before our tests were run, and there was an indication that the drag on this nozzle was lower than expected based on some smaller wind tunnel model tests. So the F-106 could be flown over a range of Reynolds number that could answer the question whether scale could account for this difference. This required some flights at a very high altitude of 57,000 feet. And at that altitude, the pilots were required to wear pressure suits, which made it a little more difficult for them to operate your controls. But your very cooperative nature was a big help. It took 4 degrees angle of attack at Mach 9/10 to maintain level flight. We kept that same angle of attack at lower altitudes by flying in turns. And down at 10,000 feet, that represented a 2.5 G turn. These flight tests confirmed that there was a trend of lower drag with increasing Reynolds number for these very sharply boat-tailed nozzles. On behalf of a lot of people from Cleveland who are on your team, goodbye, old friend. You enriched our lives. Now people can visit you, read your story, and learn of your many accomplishments.
I'd like to thank Fred and the number of people that we have here today from Lewis for reflecting back on those memories with us. Ken, if I could have the next chart, I'd like to talk about the next years of this particular airplane. Meanwhile, back at Langley, in its traditional role of doing operational aircraft-oriented research, interest began to get generated in the potential impact of lightning effects on advanced aerospace systems. Concern arose over the future of digital flight controls that might get zapped by lightning in advanced aircraft, and also the use of composite materials, which did not conduct electrical current as easily as our aluminum airplanes of today. This particular picture was taken showing some of the characteristics of lightning, or different types of lightning. The one on the right being a stroke that is going from cloud to ground. This shows a stroke that is going from cloud to ground. And it was the phenomena of the interaction of the aircraft and its system with the lightning effects that began to generate a great deal of interest here at Langley from a research perspective. The next chart showed that it wasn't just aircraft we were worried about. Spacecraft could also be impacted by the lightning effects. This lightning stroke is not as hazardous as it looks. There's a foreshortening due to the lens involved. But I do want to point out to all of the current Langley people that that was a night mission of STS-8, and the commander of that particular flight was a soon-to-be admiral, soon-to-be administrator, Dick Truly. So our administrator knows what we're talking about in terms of lightning activity. At this point, there began an issue in terms of the termination of the program at Lewis and the use of the airplane for the Langley activity. The airplane was assigned to Dryden, being a high-performance airplane, and in fact assigned Dryden's tail number, which is 816. And it looked like the airplane was going to Dryden. However, it was interceded by a number of individuals who went up to headquarters and proposed this program for Langley. And as I understand the story, Bob Summer, an ex-Langley pilot, was able to, in part, make Langley's case for the activity. We tried to contact Bob for this ceremony, by the way, and the last headquarters knows of him as he had packed up his trailer and went on a sightseeing tour. So we weren't able to tie up with Bob, but wherever you are, Bob, we thank the hell out of you for this airplane and the programs that it's brought to Langley. As shown in the next chart, the airplane entered its NASA test phase, being transferred to Langley. As part of our program, the next chart shows the patch that was assigned to the storm hazards activity. I'd like to introduce Norm Crable, who will recount some of those activities. I would like to say, while Norm's walking up here to the stage, that for you youngsters, no matter how the historians are going to record the personalities of the recent Gulf War, this was really the first storm in Norman right here.
Yes, the airplane was, quote, deeded to Dryden, and every year Ken Hodge would call up and say, "Are you done with my airplane yet?" And we'd say, "No, Ken, we need it for one more year." A lot has been said about the airplane, but I want to spend most of the time, if I may, talking about the people at Langley that I was fortunate to work with here. When Langley acquired this complex high-performance aircraft, the Research Aircraft Support Section, led by Mike Klebitz, completely rebuilt it, and Andy Plummer of Lightning Technologies, as a contractor, tested it under the lightning condition. Could I have the first view, Grant? Here the airplane is set up on blocks, isolators, and you can see some electrical and electronic equipment attached to it to simulate the effects of the lightning strike. And in this picture, the inlet covers are in, but I assure you, we tested the airplane with those covers out, with the engines running, and with intrepid crew members on board the airplane. Better to find out here than in the middle of a thunderstorm. Felix Pitts, Mitch Thomas, Bill Barden, and others developed and installed state-of-the-art electronic instrumentation to measure the lightning effects. Bob Petersons of Radio Shack developed the state-of-the-art ground weather data display system on the ground, but we also sent that weather data up to a complementary display on board the 816. Langley and Air Force pilots, led by Perry Deal and Jerry Keyser, developed thunderstorm penetration techniques in flights at the National Severe Storms Lab in Norman, Oklahoma. And the Special Projects Office provided Bruce Fisher and Roger Weinbarger to operate the instruments. Could we see the next view graph? Here's a typical day for Fisher and Weinbarger. The camera is mounted between the two crew looking aft. You can see the wingtips, and you can't see the crew members' expression, but they stayed cool due to the air conditioning. But coming off the right wingtip is a pretty healthy discharge. And you can also see, going by the canopy, the flashes of the strike as it is sweeping by the airplane. The National Severe Storms Lab sent Vlad Mazer to Wallops to coordinate the lightning data science. In Wallops Islands, John Gerlach, Jack Howard, and George Bishop provided and operated the superb Spandar and UHF radars that pinpointed storms and lightning in real time. About, I call it 200 times, somebody's got a different number, about 200 times, these people, helped by many others, worked together to send this airplane out on its mission. And they were successful 200 times. This airplane returned safely to its starting point from its thunderstorm flights every time. More than 700 times this airplane was struck by lightning. Could we see number 3? Early on, when we still had paint on it, we put a dab of primer. We traced the paths of each one of these strokes. What happens is the strike emanates from the nose and the tail, and the airplane flies through the strike, and it gets a couple of hundred more hits in it as it goes by. And we designated those hits so that we would know where the old ones were and the new ones were. Not only the fuselage, but the wing experienced these hits contrary to our expectations, and it was especially disheartening to notice that some of these swept stroke patterns were going right across the fuel tank skin. We then took the precaution of removing the paint over the fuel tank skin in the middle of the season, and then later, at the end of that season, we took the paint off the entire airplane. Let's see the next one. Well, flip to the next one, and we'll come back to that one. So there it is in the buff, so to speak. It became harder to trace the path of the lightning strikes across the airplane, but it was also safer because the dwell time and hence the burning on the skin was reduced. You don't want to burn through into your fuel tank. Let's look at that one now. These are some of the visible external effects of the lightning strike on 816. We had various kinds of fin caps. There's that black fin cap over there can be removed and replaced. Not easily, but it can be done. And we had Bill Howell at Langley build several fin caps. And the trailing edge of that fin was a favorite hang-on spot, and it got a lot of burning. And Calvin Chandler got expert in the application of 5-minute epoxy. Sometimes we flew 2 flights a day. There's the pattern of the electrical discharge around the aluminum access plate on the right side of the fin. NASA 816 holds, I believe, the world's record in the most strikes in any one flight. 72 strikes at 37,000 feet in an anvil top over New Bern, North Carolina, on that hot day in July 1982, crewed by Phil Brown and an Air Force Lieutenant, Vicki Rondo. Day in and day out, for more than 6 years during these long, hot summer seasons, these people worked together to meet the mission objectives. And they succeeded, not just barely, but extraordinarily well. For all of these 200 storm flights, it always came back. And the worst personal consequence to the crew was a bucket of cold water applied to the new crew member. And we did have new crew, both up front and in back. It was unbelievable, but qualified and knowledgeable people begged to be allowed to fly these missions. And they kept up. They had a personal interest, and they kept up with what went on the flights. We had tally sheets, number of flights, number of strikes, who had the most. During the July 82 mission that produced the 72 strikes, Bill Neely, an Air Force pilot who had flown an earlier flight that produced an amazing 15 strikes and the record to date, was standing by in Metro Operations Center. He became increasingly chagrined as his hard-won record became so totally eclipsed by the more than 1 minute action that day. The Air Force Weapons Lab at Albuquerque provided us with some high-speed transient recorders, but you don't get anything for free. They wanted us to come to Albuquerque at their weapons lab and calibrate their nuclear electromagnetic pulse generators. We had a unique national resource for determining electromagnetic transient response of aircraft, be it from lightning or nuclear explosions. Well, they weren't doing nuclear explosions, nor would I ask them to do it, but they did have a simulator. They had 3 simulators, and the next picture shows the airplane on the short one, on a short stand under the horizontally polarized dipole. And there was another simulator there, which was the vertically polarized dipole. And in some of these tests, we put the airplane on a 65-foot stand. We went out one morning to watch them lift the airplane on a... We had some pilots that agreed to try and land it if we would trundle it down the runway fast enough, but that was vetoed by the ASRB. And we decided to lift it up with a mechanical hoist. In the minute it took to convey that airplane from the ground to the cradle on top, I didn't breathe in the cold morning air. Slide off. These missions, not just the nuclear, but the Lightning and the nuclear missions, produced new data. The instrumentation designs of Pitts, Thomas, Barden, and Peterson were state-of-the-art, and these people spent much effort making them work. They were the experimenters. The missions also produced new insights into lightning phenomenology. Would you believe that those lightning strikes that I showed you a picture hanging off the wingtip stretched 500 feet behind the airplane before they broke? We learned this by virtue of the unique camera and TV systems of Phil Brown. Phil is a pilot. He is also one hell of a photo engineer. Andy Plummer, who did the lightning hardening and the ZAP test that I showed you, took these results of this mission directly to Boeing, McDonnell Douglas, Beech, and other manufacturers who incorporated them directly into their 757, 767, Starships, and other aircraft which you fly in today or will tomorrow. This was a people-intensive program, and in spite of being spread out across many and diverse organizations, inside and outside of Langley, the program succeeded because good people wanted it to work, and they worked long and hard to make it happen. And happen it did. It was an exciting and challenging program, and I was lucky to be a part of it. But I'd like to get a little bit more personal and sum up my feelings with these thoughts. Franklin started it, daring to touch the finger to the spark of the clouds. Others came after to watch and measure from afar. But we went boldly in and found out things only guessed before, and we survived because of you. Thank you.
I'd like to turn now to our last major flight activity we've had at Langley with the airplane, and the one we've just recently completed, the so-called vortex flap. If I could have the next slide, Ken, I'd like to introduce this topic. I think the technical guys wanted me to do this just to prove I knew how it worked, but I'll try and explain it to the audience. The vortex flap is an idea that the Langley researchers came forth with of a way to make airplanes that were designed for very efficient supersonic flight more efficient at off-design conditions, either transonically or at very low speeds. The problem that we were trying to fight was the fact that at these off-design conditions, these very highly swept, sharp leading edge wings tend to experience flow separation, and as the flow separates, it rolls up into what we call a vortex. This next picture that Ken's going to show you shows the Concorde, which is, of course, a very nice-looking airplane in supersonic flight, but at takeoff conditions or landing conditions shown here, you can see these vortices as they roll up over the wings, and the roll-up of this vortex creates quite a bit of drag on the airplane. In fact, the lift-to-drag ratio of the Concorde during these conditions is not much better than the HL-20 vehicle that's over on display in the hangar today. So going back to the previous chart, what our researchers here at Langley devised is a concept which, by deflecting the leading edge of this highly swept wing and designing it properly, we were able to minimize this adverse vortex characteristic, make the vortex, in fact, smaller and control it so that it moved along the leading edge of the wing. And basically, the oncoming air would see this as an increase effectively in leading edge radius and cause the airflow to attach rather than separate quite so bad. As a result of this, there was a significant performance enhancement that was predicted for airplanes that would employ this particular concept. This led to the formulation for flight validation, and the next chart shows the shoulder patch that was given to our program, the vortex flap activity, which basically focused on using our F-106 to validate this technology. As depicted by the patch itself, It was a combination of computational fluid dynamics work and wind tunnel activity, and the left wing here signifies the fact that it was confirmed in flight testing. Now I'm going to call Ron Smith up here, and Ron, you need to two-time it because we're running a little behind schedule, but I'll call Ron to come on up now so he can relate the vortex flap activity to us.
Well, I found Langley the place to come after you've done flight testing for about half of your career, a place where you can do it all, from the concept, wind tunnel testing, hardware building, design, and flight test, the whole thing. First figure shows one of Jim Hallisey's models we borrowed from the Smithsonian. It's one of the original models, the original transonic model for the F-102, which Dick Whitcomb talked about. A lot of the development that was done there was later refined by Jim Hallisey with the vortex flap, the same identical model. We're very good at long-term loans. This airplane is still on loan to us, by the way. I guess someday maybe we'll own one of our own, but nevertheless, this must set a record for long-term loans, I would say. At any rate, we tested this model and the next model, which we had to prepare ourselves. Some of the Lewis people may have wondered what happened to the other F-106 airplanes. Well, without an engine to fly it or program to use it for, and this really hurt me as an old airplane man, flight test guy, we took something like a chainsaw and cut it right down the middle, the next one, to make a wind tunnel model. Now, this is a full-scale model. That's Long Yip, who did a lot of the early wind tunnel research in the 30x60. This full-scale F-53 model, we call it, was the largest by area that was ever tested, I'm told, in the facility of 30x60. Well, before it was all done, we had done a lot of development in the wind tunnel. We had 4 models built, this being one of them, and the other one you saw, 2 others, 4 models. We had 6 wind tunnels that we went into and 12 individual wind tunnel tests. I don't know how many hours that amounted to, but it probably is comparable to many of the time spent for developing an entire airplane. One of the new fighters rarely gets as much attention in the wind tunnel and precise attention as this particular concept did. Now, it's an easy step to go from concept and a few wind tunnel tests, but I should stop here and tell you what happened early on. Langley has something they kind of call an informal peer review. That's where all of your friends who don't really believe that concept that Joe showed about how well that would work and aren't happy with just a few computer runs, they want to be convinced. So we had almost a year of peer review where everybody who really didn't believe that concept took a good shot at it. We still went ahead with it. I mean, they recommended we go ahead with it, and furthermore, when we took it to industry and had their review of the concept and what was needed, they highly recommended a flight experiment. So somewhere along there, we decided to go ahead with it. Here is what we did in the facility right here. We did all the hardware right here at Langley, the design and the building. Now the concept is over by the airplane. You see the piece, the portion of the flap is just in front of the wing there. Jim Campbell early on said, it's elegant in its simplicity. It was simply a triangular shape that was attached to the leading edge. We were able to ground adjust it by a piano hinge affair, which could be adjusted on the ground and set at 4 different positions. So it was, we could set 4 angles and fly each one of them separately in flight. Here's one of them. It may be difficult to see this. Here is the flap itself, a portion of the leading edge. And of course, there were 2 of them. Here's the tip and the trailing edge. We were a bit concerned about taking a very old airplane and attaching something like that to it that was experimental, strictly experimental, even though we had great confidence in the design that went into it, the aerodynamic design. But Garland Goodwin, who was one of the principal designers for this, for the flap itself, he assured us all at one of the safety review meetings, he said that, well, it's hell for strong, which gave us a lot of confidence. He went through all the numbers and he assured us the flap was hell for strong. The thing we were concerned about is what the structure internally was, how sound it was. So we after we had built this, next figure, oh, small item. On the order of, well, there's about 120 people there who showed up for when we were just getting into the FLAP program before we'd actually flown to pick up their patch. We know of 250 people that were touched by this program in some way. They weren't all employed full-time, but Langley was the sort of place where you could start out with a handful of designers, a few wind tunnel people, computer work people. They'd do their job, we'd move on to the next group. So over the span of almost 10 years, we figure about 250 people were touched by this project, and they all did their excellent job. Good. Well, here's the airplane out on the ramp with the flap on. We strain gauged it pretty thoroughly to assure ourselves as we flew that it had integrity. We had developed a real-time analysis technique so we could actually observe the strains as the airplane was maneuvering. We also had an extensive array of pressures. These belts contained pressures which completely covered one side and most of the other side so that we could correlate directly the pressure distributions with the predictions that we had from the wind tunnel. Next page. Well, here's another one. Generally, a flight would stage here from Langley, and we would fly our ground monitors to Wallops Island. And this just shows the kind of commitment to duty. This is one winter night for the flow visualization where we mounted a light source and a series of cameras so that we could actually, and a smoke system, so that we could actually see the vortex moving about the wing as we flew. We had to fly at night, and hopefully on nights where there wasn't any moonlight. So there are many cold winter nights that Langley people were out here doing the flying and the testing and the data retrieval, which maybe is a little more than required in duty, but we got the data. Next one. Well, I got to say something about this one. Norm Crable alluded to Phil Brown's capability as a cameraman. He's an excellent camera engineer and a good photographer. Well, on occasion, when we had to go to Wallops, and this was a winter picture, we had to have an airplane to take us over there, bring us back, a pilot for that, a pilot and a backseat driver for the F-106. Well, it came finally that we were down to one support airplane, the others having to go through their regular inspections. Well, I got a little testy and I said, look, the F-106 is ready, the instrumentation is ready, everybody is ready to do this flight, let's get on with it. Well, operations, who always gives us friendly support, went as far as they could, and I said, well, look, Ron, the only thing we have is the helicopter out here. I said, well, that's all right, what's wrong with the helicopter? He said, well, first of all, only 3 of you can go, and you're gonna have to put on these, let me get this right, cold water immersion suits. This is a one-size-fits-all rubber gadget, and as you can see, some of us look better than others. I know Merle looked particularly well in this picture. But Phil came out and he says, oh, before you jump in the helicopter, he says, I want to get your picture. He says, just hold hands. And this is what we have now for posterity. Well, I have this up here. JR, who represents engineering, I got to say something about engineering. From day one to day last, they stayed with the project, they did the design, stayed with the fabrication and the flight testing. I don't think they expected to follow all the way through, but for integrity's purposes, and of course he was very friendly, as you can see, with the hand-holding and everything. He carried it through for engineering all the way. And the fellow on the right, I mentioned just briefly, I got to say that my right-hand man in this flight experiment was a woman. It was Merle Ott, and you may recognize her. She looks a lot better today, but that's Merle on the right. Okay, slide off. Well, I was to find that, well, first of all, the results. First of all, we've been talking to industry. Jim Hallisey and others on the team have taken the data to industry directly, and we always, in NASA, we generally work that way. And what I can say is we now understand and can supply design rationale for a vortex flap, which was far from what we could do about 10 years ago when this started. And Langley is unique as a place where you can do that from beginning to end, and then to hand the work over to the industry so they can incorporate it in the next generation aircraft. So thank you. Thank you all.
Next slide, please, Ken. One thing I want to do before I forget is to extend our thanks to the Air Force. Throughout the F-106 operation here at Langley, the Air Force has been a major supplier of spare parts, excellent relationships with us. It started with the 48th Fighter Interceptor Squadron here at Langley when they flew F-106s, and of course the fleet's been upgraded to F-15s. Then we started drawing on the New Jersey Air Guard, and they switched over to F-16s a couple of years ago. So just a note of thanks to the Air Force for all the support through the years that they've given us. Next chart shows the end of that last flight that we made back on April 30th, where we officially made the last flight. We completed over 90 flights with this airplane. Fred said they completed 300 at Lewis. We did 90 flights. We intended to do 30 when we started the program, but that's research for you. This scene shows the traditional water soaking for the pilots and the managers. Phil Brown already had his, and this shows Dan DiCarlo getting doused by Calvin Chandler. Frankly, the reason why I'm so happy is because division chiefs here at Langley usually get doused with some other material besides water, so I was delighted. At this point, what we'd like to do is bring up to the stage Earl Dunham, who's going to make a presentation to one of the most loved employees we have in our division, who's been with this airplane and made it go for all the years. Earl, if I could have you up. That slide, Ken. I have the pleasure here of honoring one that's so dear to us here at Langley, Merle Ott. Merle's been with the airplane since he came to Langley and has worked all the programs that were done on it. Merle came to Langley in 1949 as a math aide and engineering technician in the full-scale wind tunnel. In 1958, she came to the hangar here to work flight test programs. She's worked flight test programs such as the SH-3 helicopter, CH-54, CH-53, and 204B helicopter. She worked on the Hawker Siddeley P-1127 VSTOL jet aircraft. She worked on the Boeing 737, and finally, for the last 12 years, she's worked on the 106 aircraft here. Merle has 42 years of government service, and along with the aircraft, Merle has decided to retire too. Now, I've known Merle for most of the 25 years that I've been here at Langley, and I respect her as a co-worker, I value her as a friend, and I trust her as a confidant. And I find out that my situation is not unique. There's a large number of people, even in this audience here, and others at Langley, and those who've retired from Langley, who also find Merle to be one of the valued people that they've been associated here through the years. So, Merle, if you'd come up, after 42 years, it's my pleasure. There you go. Merle, it's my pleasure to present to you the NASA emblem here, insignia, and invite you and your family and friends and co-workers to join us after the picture-taking session. The Friends of Langley, of Merle here at Langley, would like to present her with additional gifts and memorabilia and some things we think you can use in your retirement. And we will gather here after the photo session over by where the view graft is. Okay? Thank you. What about the future of the F-106s? If I could have the next slide, Ken. We had to wage a little bit of a war with the Air Force. The F-106s, as they're being retired, are being used for unpiloted drones, as Pete alluded to earlier, to be shot down in practice by some of our current and future fighter airplanes. The drone program, this shows a photograph of a Montana Air Guard airplane that's been retired. If you look closely at the cockpit, you'll see there's no pilot there. The airplane's being flown by remote control from the ground, and in this case, being hunted down by F-15s. 194 of these F-106s are going to be modified under a contract by Honeywell, and they'll be used in air-to-air practice at Eglin Air Force Base down in Florida, and ground-to-air missile activity out at White Sands in New Mexico. So we had to quickly scoop this airplane out before the Air Force got it back and decided to use it for target practice. We're happy to say we succeeded in that, and the next chart shows where this airplane's going. As I mentioned earlier, this is going to be a world-class Air and Space Museum downtown in Hampton, Virginia Air and Space Center. The next slide shows the artist sketch of what that facility will be looking like when it's completed. As most of you know, it will be completed in spring of next year. The plan is to transfer this airplane to the museum probably in the October timeframe, so it'll be on display in the museum when it opens next year. The next slide shows that some of the tenants are already moving in. The Air Force had an F-4E from the Vietnam era that they were able to get into the museum before the walls went up. Unfortunately, we were still doing research with ours, so we couldn't get it before the walls went up. I understand the plans are to have something on the order of 14 aircraft displayed in that museum. I think it's 110,000 square feet of area. So there will be quite a display there. The next picture is an aerial view of downtown Hampton, giving you an update on what the facility looks like. For your information, our airplane, the F-106, will be hung from the ceiling and will be displayed adjacent to a second floor balcony for all to see, ironically very similar to the X-15 as it's currently displayed at the Air and Space Museum. So two airplanes which were born at the same time will ultimately be displayed in the same way in the museum status. Now at this point, I'd like to introduce Mr. Peterson again, who will make the symbolic transfer of the airplane over to the museum.
Thank you, Joe. I see you've got a normal NASA overrun. We've heard a lot about the history. Now it's time to get to the future, as Joe mentioned, and to transfer this airplane to the new Virginia Air and Space Center. And I have Tom Chisman with me here on the stage, and Joe's going to bring something up. Tom, this is the control column from the aircraft. 816 pilots over the years have used this to change the aircraft's speed and direction. In much the same way, you're taking this control column will symbolically represent the passing of NASA 816 from NASA to the Virginia Air and Space Center.
Pete, Joe, all of those here who have been associated with NASA 816, I would like to say thank you. Joe told you about the attributes of the plane if it were a woman. He'd also told you some of the downside. I would only remind you, Joe, it's probably the fastest lady you ever retired too. But on behalf of the board of directors of the Virginia Air and Space Center and the Hampton Roads History Center, I gratefully acknowledge the NASA's contribution again, as I continually do almost every day. Thank you.
Handing over this column is more than passing a baton. It signifies the end of one era and the beginning of another. We are really looking forward to that grand opening next spring. Our thanks to the Virginia Air and Space Center, the City of Hampton, the Commonwealth of Virginia, for ensuring that the exciting story of NASA 816 and its flight research teams will be shared with the hundreds of thousands of visitors that magnificent new facility will host over the coming years.
Just a few closing comments. At this point, I'd certainly be remiss if we didn't recognize some special people that made this ceremony all come to pass. Paul Stow, if you would stand, and if everyone would hold their applause until I introduce about 4 people. Paul is responsible for that super brochure that you received. I'm sure the the new museum would take a look at that in terms of offering for sale down at the premise. Pat West, my right-hand man. Where are you, Pat? Where are you, Pat? Is Ann Suit there? Oh, they're over at the refreshment table. They're shy. Keith Henry, are you around? There's Keith. These people all came to all our meetings, helped set this up in terms of its administrative and organizational details. Mike Klebitz. Mike was an ex-crew chief of 816. He knows the airplane. Thanks, Mike, for directing traffic here in the hangar and making sure this all came to pass. Andrea Lewis was over at the refreshment area. Thank you for your help and all the supporting cast that came into this in terms of electronics, visuals, etc. Thank you so much. Before we end the ceremony, I want to remind you that we'd like a photo session. It isn't raining, so we'll pull the airplane out of the hangar into the apron, and we'd like to take a picture of the Lewis team with the airplane, the Langley Storm Hazards team, the Langley Vortex Flap team, and if we could, Mr. Peterson, Mr. Chisholm, and Dick, we'd like to take individual pictures of you people with the airplane. Basically, in closing, I'd like to summarize saying it's difficult in even an hour and a half to summarize 30 years of research. I feel compelled to comment doing the research and background on this thing to give you a little bit of my feelings on the thing. The challenges that were faced by the various research teams using this airplane were extremely monumental. Nothing came easy to these people. And the results, as you can see, were world class, whether they were here at Langley, at Lewis, or any other place. It really speaks well of the NASA spirit and the NASA dedication. They were done at minimal expense. They were done with maximum dedication and safety. The more I dug into these stories, the prouder I am to be associated with the people that you heard and the guys that have worked on the program. I want to thank everybody for coming, and I hope that all of you have been part of the F-106 story. Will enjoy telling your children, your grandchildren, and your great-grandchildren when you go down to the new Air Museum, your part in that F-106 program. So to all the people on all the teams, from the engineering and fab guys to the crews, the pilots, the engineers, the data acquisition types, flight ops, safety inspectors, all of you. Fellows, you did one hell of a job. Congratulations. Now, if you would, I'd invite everyone to join us for refreshments and for this photo session. Thank you for coming.
A tribute to NASA 816 and the NASA 816 team. This historic aircraft made many outstanding and unique contributions in its more than 30 years of service, both with the Department of Defense and with NASA. As you'll read in the souvenir pamphlet, the Air Force used NASA 816. Of course, they didn't call it by that name, to evaluate new modifications before they went on to the fleet airplanes. Lewis Research Center used 816 to study supersonic propulsion systems. Langley first flew 816 to study the effects of in-flight lightning strikes on the aircraft, and then to study the aerodynamic effects of a wing modification, all of which you'll hear more about later. In addition to its significance as a test vehicle, this aircraft just made the last manned flight of an F-106. The Air Force F-106s have been converted to target drones. They are still flying unpiloted for obvious reasons. As you'll hear later, this aircraft design has special significance to Langley Research Center. Langley's Richard Whitcomb, who is here today, was instrumental in reshaping the aircraft that would eventually become the F-106 resulting in a revolutionary advance in aircraft design. I want to welcome everyone to this special gathering and recount with the people who were there, the story of the F-106, and in particular, this unique airframe. To bring you the first part of that story, here is Joe Chambers. Joe?
Thank you, Pete. This occasion is historic, very historic, for three different separate reasons, as Pete alluded to. First, this is a story that you rarely see in aeronautical history, the fact of the last of a 35-year run of production airplanes returning back to a research lab that had a significant impact on the development of the aircraft. Second, this specific airplane, through its career, exemplifies the capabilities, the innovations, the dedication of NASA, not only here at this distinguished research center, but also our sister center, the Lewis Research Center, and of course our brethren, the Wallops Flight Center as well. The third historic occasion is that we will symbolically retire this airplane today to a world-class, up-and-coming air and space museum right here in our own backyard in Hampton. And it's a pleasure for NASA to be able to make this action. Now, to get into the agenda and the program, what we're going to try and do, I'd ask you to look at your the black insert in your souvenir program. For those of you that are colorblind, it's still black. I do have one minor agenda change to make here. Jim Day, the F-106 Convair rep, has a conflict. Couldn't make it with us today, but not to fear. We've done the homework, and yours truly will cover the Air Force years. At the onset, I'd like to say I'd love to have everybody associated with each program cross the stage, but I don't think it would bear the weight. So we've chosen a representative, although not unworthy person, to be able to come up and talk to the programs. So I hope you enjoy that. Over the next hour, basically, as you can see in the agenda, what we'd like to do is retire one of the most important legends and retell one of the most important legends in aeronautical history in this country, and certainly at the Langley Research Center in terms of area rule. We'd like to trace the history and some of the technical programs that this particular airplane has been involved in throughout its distinguished career, symbolically retire this airplane to the new Air and Space Center. And as part of this process, we've taken the occasion to retire one of our most loved NASA people who have made this airplane go for the last history since it's been here at Langley. And finally, before I forget it this time, I want to remind people that after the ceremony, there will be a photo-taking session by the airplane, and I'll say more about that at the end of the program. So you can see we've got a lot to do to squeeze about 32 years of history into about an hour. And I've asked the speakers to try and keep to their time on penalty of death. Norm Crable is sitting over there saying, yeah, Joe, I know. I'd like to begin talking about the airplane itself. In my 29 years here at the center, I've retired a lot of people emceeing retirement parties. But this is the first time I've ever retired an airplane. And all you females out in the audience, I'm sorry, but you'll have to provide me the liberty of referring to it as a her. And with that history of retirements in mind, I've got to look at it as I would a female that I'm retiring from the Langley Research Center. The airplane itself, when you look at it, first thought I have is that this is going to be the heaviest female I've ever retired. Interesting, we don't need to take the time to do our usual presentation of NASA wings or NACA wings, because this retiree brought its own wings today. Even though she's 30 years old, it's a beautiful airplane. You can see the curves, the Mae West or Marilyn Monroe waist on the airplane, which is really a statement of the ability of our crews to keep the airplane in such a pristine state. So although she's over 30 years old, which is probably 400 years old in dog lives, it's a remarkable airplane. But we all know that retirement parties have to be a mixture of kudos and a little bit of roasting. So when I look at this airplane and again think of some of the females I've retired, I just have a couple of observations. First of all, for a female retiree, boy, she really needs a nose job, no question about that. And I don't know how many of you are really aware of the vices that this female has. She's a habitual heavy drinker, very high octane fluids. And probably the most embarrassing vice that this retiree has is the fact that she's always really had a real bad problem with exhaust gases. We'd like to start off the ceremony by recalling one of the most important aeronautical legends here at this center, the one that Pete alluded to earlier involving Dick Wickham and the development of the area rule. By way of introduction, I'd like to say a few words. This story begins back in the 1950s, so for all you younger people, we older people will turn our heads so you can return to the womb, because this was long before you were a gleam in somebody's eye. But the story really involves three different ingredients. The first was basically the general interest and, frankly, the unknowns in how best to shape airplanes for high-speed flight. The second one was the development of testing techniques to get good, accurate prediction of aircraft performance at transonic and supersonic speeds. And the third was basically a widespread paranoia and perception of a general threat to the United States from the Soviet Union in terms of nuclear bombers. First, I'd like to talk about the issues of high-speed airplane design. This first slide indicates some of the thoughts that went into how airplanes were proposed to be designed for high-speed flight. This basically shows an idea of the Convair company. They had a great interest in looking through the German World War II data in highly swept wings, and in particular some of the German information on delta wing airplanes. The Germans never flew a delta wing airplane, but they were able to, the Convair company was able to work with some of the Germans, in particular Alexander Lippisch, the designer of the Me-163 rocket-powered airplane from World War II, and basically designed this airplane to evaluate the handling characteristics of delta wing airplanes. This is the XF-92A. It was put together from 5 different airplanes to try and hurry the program on, and it basically was restricted to subsonic flight, made its first flight back in 1948, and flew quite satisfactorily in terms of its handling characteristics. So the promise of the delta wing as an input to overcome the hurdles of high-speed flight was predominant on the list of thinking in the U.S. at that time. However, along with that was the concern over accurate projection of transonic performance, in particular drag prediction. The next chart shows two things that I want to mention about that era. The first is that there was considerable concern about wind tunnel testing to measure transonic performance. As most of you know, the Langley Research Center in that same time era had developed a slotted configuration for the 8-foot transonic tunnel, achieving the Collier Trophy Award to Langley for that achievement. However, there was still great concern about the fact that wind tunnel walls reflected shocks and basically gave erroneous data at transonic. I'd like to welcome everybody to our party. My name is Joe Chambers. I'm chief of the Flight Applications Division here at Langley. And it certainly occurred to us as we reached the end of a 32-year career of this illustrious airplane that it certainly wasn't worth just rolling it out the door, and decided to have a little celebration. And I hope all of you enjoy it, have a good time, and maybe learn a little bit something about the F-106 and about our airplane in particular. I'm glad everybody showed up. We've got a few guests that I hope show up late. That's some of Norm Crable's storm hazard, severe storms. I hope they show up after we're through this afternoon. At this point, what I'd like to do is introduce Richard Peterson, the director of the Langley Research Center, for his welcome comments.
Thank you, Joe. Let me add my personal welcome to all of you here today. Welcome especially to everyone who worked with this historic aircraft. While we're focusing our attention today on the flying hardware, the aircraft we at Langley call NASA 816, the real kudos go to the men and women who made it possible for 816 to fly and to do its work. We're honored to have many of them here with us this afternoon. We're also honored to have several special guests with us, including the Mayor of Hampton, Mayor Jimmy Easton, On my sheet is the Vice Mayor, Mel Butler, and I haven't seen Mel. I hope he does get here, but he may not. He's an old friend of ours here at Langley. And from the Virginia Air and Space Center, the president of the center, Tom Chisman, the director of the center, Ralph Johnson, and board member Ray Bottom. We also welcome a number of guests from the Air Force, from NASA headquarters, the Lewis Research Center, Wallops Flight Facility, and the Smithsonian National Air and Space Museum. We're pleased that you're with us this afternoon to pay